Hi guys, I am hoping that our distance learning starts well, and we'll see how this video goes. But for third hour, this is a review. You guys have written these notes. For sixth hour, these are new, so you may need to pause this video as I talk and write things down. So just kind of do what you need to do to get everything written. I'm going to go through it pretty quickly, otherwise this video will last forever. So thermodynamics is a field that deals with energy, specifically in the form of heat. How that heat is generated by chemical reactions or what is needed to cause the chemical reactions. Energy is a huge deal, and the heat that it produces is really what we're dealing with thermodynamics. And so knowing about the energy, the heat, is important. Knowing about temperature and how those temperatures change and how they are affected are all part of thermodynamics. Now, when we measure energy, you'll recall hopefully from freshman year, we always used the unit joule, and that will continue to be our unit. We may use kilojoules in some cases, but we're dealing with joules. That is the SI unit. Another unit for energy is a calorie. A calorie has an equivalent to a joule. We could do a conversion, we probably won't. But just be aware that 1 calorie is the energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. That's the actual definition. Joule deals more with actual energy itself. Now, our first real concept to deal with is enthalpy. Enthalpy tells you what is happening during a chemical reaction. It is the measure of the heat content in a system. In our case, that's a chemical reaction, a chemical equation. And the real thing that we want to deal with is the change in enthalpy. And this is a calculated value. It has some meaning to it, especially knowing if it is positive or negative. The formula is very easy. It is delta H equals H of the products minus H of the reactants. You will use that formula quite a bit in different parts of this unit. All right, now exothermic reactions. You guys know exothermic reactions are when heat is given off as a product. In general, this is done so that you go from a more unstable situation to a more stable situation with lower energy. And so that is what this graph is showing. And it is showing basically this drop here, this green arrow that they have is where heat is being released. So heat is going out. That's what we detect for exothermic reactions. And if you calculate using our formula from before, if we say that the reactants have 50 kilojoules, whereas the products have 10 kilojoules, using our formula of products minus reactants, 10 minus 50, that gives us negative 40 kilojoules. Oops, my negative sign's not there. And that negative sign is the big thing. Exothermic reactions are always going to be negative. So kind of remember that as we go through some of the other parts of thermodynamics. Now, endothermic reactions are going to look exactly opposite as far as the graph goes. This arrow, red arrow going up, means that heat is going into the reaction. So we're heating up the reactants in order to produce the products. These typically, if you felt them, would feel cool because heat is going in. It's basically absorbing or taking energy away from the system or from the surroundings, to cause the products to form. Same problem that we had before, but now I've switched them. If you have 10 kilojoules for your reactants and 50 for your products, if we do products minus reactants, 50 minus 10, that gives us 40 kilojoules. So I'm not super good at writing this. And it is a positive value. Endothermic reactions will always have a positive delta H. Now, for sixth hour, that is kind of the end. Oops, almost. That will be what we cover today mostly is enthalpy. I do want you to know how to calculate it. And so this is delta H. Remember, delta just means change in, and it involves energy that forms a compound. you will need to be able to calculate delta H and tell me if the reaction is exothermic, and remember that means it's a negative sign, or endothermic, and remember that means it is a positive sign. If you are given an equation like this, you can actually do some math. The big thing to remember, first of all, is that these are the reactants and these are the products. Now, I'm going to pause my video real quick and actually write down the problem and the example, and then I'll go through it. Okay, so I have the numbers written down for each of the compounds that are written in the equation up above. Now, I have attached a reference chart to the email that I sent that has these values. It's a huge chart, 20-something pages. You're going to need to use it to find these values, and I'll try and work out a better system, but for now that's where that kind of comes from. So if you look on that chart, there should be a column that is labeled with delta H symbols, and for each of these compounds they will be listed. And so if you look for CO2 in the gas form, it will have an H value of negative 393.5. And so each one you'll just look them up. A few things to make you aware of: if there is a coefficient like this 2, then you will multiply the value, in this case for water, times 2. So look and see if you can find all of these numbers. Check back with me if you can't, and we'll figure it out. But anyway, doing the math, you end up with negative 885.5 kilojoules per mole. These units come from, or you can look at the chart. That's the units for H. Excuse me. And the big thing that we're really actually worried about is not the actual number itself, but more the sign. It is negative, which tells us that it is an exothermic reaction. All right, and you guys, in 6th hour, this is what your practice will be today. Okay, so I'm going to move on and do entropy in the rest of this video. Feel free to pause and come back as you need to. All right, so entropy, is a measure of the disorder in a system. In nature, everything wants to use as little energy as possible, which means less order and more disorder. And this is a natural law. It's one of the laws of thermodynamics, and it is part of the energy system in the world because it's trying to get rid of energy, essentially. Delta S is the representation for entropy, and it is also important as far as the signs, just like the delta H is. Positive, you're increasing disorder; negative, you're decreasing. Now, with entropy, there are rules. You don't necessarily have to calculate it, but you can, and we'll talk about that in a minute. But you can also basically go through some different characteristics. If you increase the temperature, disorder increases because the particles are moving more. If you dissolve a solid into a liquid, the solid particles become dispersed, and that increases disorder. But opposite, if you put a gas into a liquid, you are basically confining that liquid, and that makes them more ordered, and a decrease. Changes in state: if you go from a gas to a liquid to a solid, if you look at the relationship, a gas has the most disorder. You know that just because of how the particles are moving. A solid has the least disorder because they are very organized. All right, and then last but not least, if you separate one compound, like water, into its individual parts, you are going to have more disorder. It's just more to keep track of, basically. All right, now you can also calculate entropy. So just like we did with delta H, on the reference chart that I am sending you, there are values for S. So you can and you will actually do the exact same type of problem as the example that I just did a few slides ago. You would use the same chart. You'll do the exact same thing, products minus reactants. Now, with a equation, you also could maybe just look at it. If you look at what is happening, for instance, in this first one, if you're going from a solid to a gas, you are increasing disorder. That's supposed to be a positive. So you have an increase in entropy, so you have a positive S. Same with this bottom one, you can look at it. If you take two things and you combine them, you put them together into just one thing, you're actually decreasing your disorder. You're making things more orderly, so you would have a negative delta S. Again, it's kind of common sense. If you look at it, you just have to kind of keep it straight in your mind as far as how the signs are going. All right. Now our next thing that has to do with thermodynamics is spontaneous reactions. Spontaneous means that it just happens. Reactions that happen as written are considered spontaneous, and there are two conditions that need to be met. First of all, it has to be exothermic. The numbers don't really matter for us, it just depends on if it's negative or positive for delta H. And then with the entropy, as long as disorder is increasing, as long as you have a positive delta S, then that is spontaneous. So those two together mean it is spontaneous. Non-spontaneous, of course, would be the opposite. Now, I do have my little disclaimer down here. If you have two negatives, negative delta H and negative S, or two positives, it really will depend on which one kind of overbalances the other. We will not deal with situations like that, but I just want to make you aware that it's not always negative or positive. All right, now free energy is actually what we can use to determine if a reaction is spontaneous or not with one number instead of H and S. Delta G is the symbol for a change in free energy. If delta G is negative, you have a spontaneous reaction. If it is positive, you have a non-spontaneous reaction. And look, there is our same old formula, products minus reactants. The reference chart has information on that also. Again, you'll be doing some practice problems. Just be aware. All right, now, the last thing for thermodynamics involves changes in state or changes in temperature. Changes in state, remember, involve going from solid to liquid or liquid to gas. And these can be calculated using constants and if you know the mass. The heat of fusion is how much is needed to melt 1 gram of a substance. The heat of vaporization is how much is needed to boil 1 gram of a substance. There are tables upon tables of information about how much heat is needed for all kinds of different substances. We, for the most part, will use water just because it's easy and pretty common. It goes through all 3 states of matter. But the formulas themselves are kind of the important part for us because I'll always give you the constants. If you're calculating heat of fusion, you will have it equal to Q. Q represents heat or energy, and it is equal to the mass times this constant, a heat of fusion. And then the same, sorry, my printer just went off. Same thing for heat of vaporization. You have the formula mass, whatever the grams are, times the heat of vaporization. All right, now, last thing, specific heat. This is the heat that is required if you're going to raise 1 gram of a substance by 1 degree Celsius. So to find specific heat, you're still having everything, you're finding Q essentially, which is energy. You have the specific heat, which is a given constant. Again, I will always give those to you, times the mass, and then times the change in temperature. So if it goes from 30 degrees to 40 degrees, the change in temperature is just 10 degrees, just the difference between the two. Now, if you recall, back a few units ago, we had this graph. This is a phase change diagram. The Q formulas that we just talked about represent or correspond to different segments on the warming curve in this case. You could also put them on a cooling curve, and they can be used to actually determine how much energy it took to melt this ice and turn it into a gas, or whichever phase that you are trying to find, or whichever substance or state of matter that you are trying to heat up. You can use those 3 formulas or a combination of them or just one of them to find the actual value for energy. So we have one example left to do, and it is the biggest problem that you will ever have to do with all of these Q formulas. I will, again, pause this and get everything written, and then we'll go back through and go through each step. Okay, so first things first, I would always start with drawing the diagram and basically tracing where the temperature changes, or what is between the two temperature changes. So we have, we're going from -10 to 105 degrees Celsius. So we're down here at the bottom of this graph. First of all, we're starting at -10. Water freezes / melts at 0 degrees and boils or condenses at 100 degrees. Those are my other 2 points that I wrote on here. But we're going, first of all, a first step from -10 up to 0. And that is our first formula. The Q is SP times M times delta T. Then we are going to melt it in that segment, which is Q equals M times HF. And then we heat that water up. It's a liquid now, so we heat it up. And so we're going to use this formula again, and this time use the SP for water. And then we boil it. So then we use our last formula, the Q equals M times HV. And that gets us up to steam, and then we're going to heat our steam up 5 more degrees. So we're going to go from 100 up to 105. So we use this formula again. Now on the next page, I will write out all the numbers, show you all the math, get everything kind of added up. Again, ask me if you have questions. Okay, so here are all of the steps written out. I tried to color code them. I hope that helps and doesn't make it more confusing. But if you remember, we were going from -10 all the way up to 105 up here somewhere. So the big thing to point out, first of all, are these temperature changes for the SP times M times delta T. This temperature change is just the difference between, in that first case, -10 and 0. So that's where I get the 10. The second temperature change is the difference between 0 and 100. As I boil the water right here, that's 100. And then that third temperature change down here, this 5, is the difference between 100, which is where water would boil, and the 105 is our final point. So that's where those come from. That's probably the biggest mistake I see on these problems, is making sure you get the temperature in the segments that you need it to be. Other than that, you plug in using the constants that I have on the previous screen. Multiply everything out, and then your actual answer is the addition of all of the segments. And like I said, this is the longest problem that you will work using these formulas, going from all the way down here at the solid level all the way up to a gas. That is the longest. You could just go from a liquid to a gas, which would involve 3 segments. You could just boil something, which would involve 1 segment. So these problems are kind of, you kind of have to make sure you know how many steps to do. And using this graph is one of the easiest ways to do that. It helps you have kind of a visual of what you're doing. All right, that is thermodynamics. For 6th hour, I know this is all new material. You'll break it down, kind of group day by day, different parts of this video. For 3rd hour, this should have been a review. Hopefully I got the problems right. And it is just for you to kind of go back over it if needed. We will do some more practice. We will continue to review. I will try and figure out how to do a test over this stuff online, and we will carry on. Now, the last thing that I want you to be aware of in both classes, 3rd hour and 6th hour, these are things that I want you to put on your periodic table. I want you to continue to use your periodic table as a reference. I know from here on out, you're going to be at home, which means you're going to have all kinds of references, and that's fine. But I do want you to continue to kind of build on your periodic table so that you can use it hopefully in the future in other chemistry classes that you might take. So these are what I would suggest. The formula is pretty much all the same for these three. You know, it's just products minus reactants, basically. The values, excuse me, I would list out, excuse me, that negative delta H is exothermic, positive is endothermic, positive S, you know, negative S, what they all mean, and then know the conditions for a spontaneous reaction. You may want to also, and I forgot to put this on here, you may want to also be able to recognize a graph for exo versus endo. So look back in these slides, or look back at your notes, and just kind of see the general shape so that you would know the difference. Okay, as always, ask me questions. Hopefully this will get better and we will get it figured out, and you guys will keep up with chemistry because you're doing great. I'll talk to you later. Bye.